This is a lecture about how the periodic table is organized, and it serves kind of as a prelude to chemical bonding and chemical reactions. Of history, the concept of the periodic table and the fact that some of the elements have properties that are similar to others started with a scientist named Mendeleev, and he took the elements that were known at the time with their list of properties and organized them, kind of laid them out and organized them in a certain way. And he noticed that if he organized them in a certain number of rows and columns, that he saw similar properties from within a column. And so he thought that the key to ordering them was to list them in order of their mass. And when he did this, he did see recurring properties. Recurring is really another word for periodic, some pattern that occurs on some type of regular basis. So bottom line, Mendeleev was the first one to come with a periodic table, and it was based on mass. You'll see in a minute, if you haven't already noticed, that our current periodic table is arranged by atomic number or number of protons. All right, so from Mendeleev's work, we came up with a law, and you might remember from our first unit that a scientific law is simply something that has been developed over years and years and years of observations that seem to always hold true. And so the periodic law says when the elements are arranged in order of increasing mass, certain sets of properties recur periodically. So Mendeleev's table, obviously not that many elements were known in Mendeleev's time. There were a lot of gaps in his table, and whenever there was a gap or a hole, he assumed it was an element that was missing that hadn't been discovered yet, and it allowed him to predict some yet undiscovered elements. In our current periodic table, elements are listed in order of increasing atomic number, okay? That's the number of protons. Now, for the most part, the vast majority of elements, when you lay them out in increasing atomic number, they're also laid out in increasing atomic mass. So the modern periodic table isn't grossly different from Mendeleev's, but there are a handful of elements that have a higher or lower mass than expected, and so there were a few swip-swaps going to the modern periodic table. So here's a look at our modern periodic table, and just kind of show you, it is organized by atomic number. So it goes 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay, so it's ordered by the number of protons the elements have. And it turns out that elements that are within the same vertical column, which we call group, do have similar properties. And so it's actually amazing what we can get out of the periodic table. I always call it the student's giant cheat sheet if you know how to use it correctly. All right, so some of the classifications of the periodic table that will help you. One important dividing line is what we call the stair-step, and you see it's over here, this red line. And the stair-step divides the metals from the non-metals. And so everything to the left of the stair-step are metals, okay? Including the middle section, they're called transition metals, and the bottom section, rare earth metals, those are all metals. To the right of the stair-step, we have nonmetals. Okay, so if I were to ask you a multiple choice question and say most of the elements belong to what category, you would answer metals, hopefully. And these unique elements that touch the stair-step, there are 7 of them, are called metalloids. They're also sometimes called semimetals. Okay? They have properties in between the metals and the nonmetals. And so that's our probably most basic division of the periodic. Some of the properties of metals, and you should have these basic properties down. They're good conductors of heat and electricity. I'm sure you're probably already aware of that. You don't want to be touching or standing on a piece of metal in a lightning storm. And you also don't want to be touching, let's say, the hood of a car when it's 100 degrees outside. They conduct heat and electricity very well. They are very malleable. That word malleable simply means you can kind of mold and bend it. Most metals can be. Ductility, kind of a weird word, but you see most of our wires are made out of metal because they conduct electricity so well. And lucky for us, they have the physical properties of being able to kind of be drawn or stretched into a wire shape. They're usually shiny and very important when we get to chemical reactions, so make sure you know this one I've put in orange. They tend to give up electrons, okay, which means they have low ionization energies. They tend to be readily donate their electrons to another element who wants them more. Nonmetals, on the other hand, kind of the opposite of what you can think of for the properties of metals. There are only 17 nonmetals. They can be any state of matter, whereas metals are virtually all solid. There is one exception. Mercury metal is a liquid, but the rest are solids. But nonmetals can be solid, liquid, or gas. They are poor conductors of heat and electricity. They are not bendable and moldable. They actually tend to be, if they're solids, they tend to be brittle. Rather than wanting to give up electrons like metals do, they are greedy. They would rather gain extra electrons. And then, of course, the metalloids, those 7 elements whose box in the periodic table touches the stair-step. They exhibit properties that lie someplace in between metals and nonmetals. These turn out to be really valuable elements in industry because they're classified as semiconductors. You might remember metals are conductors of electricity and heat. Nonmetals are non-conductors. It turns out that metalloids are semiconductors. You may have heard that term when somebody's talking about a silicon chip. That is the type of chip that's typically used in computers. You may have heard of Silicon Valley, the area of the country that produces these, but that's a tremendous source of money for industries, is using silicon, the element silicon, which is a metalloid, as a semiconductor. And what that means is these tiny little microchips that go in our tiny little phones and other microcomputers. We want them to have. We want them to conduct electricity. That needs to happen to be a microchip, but we don't want them to be so conductive that they short things out. So the metalloids tend to be perfect for that. All right. So other divisions of the periodic table, just to be able to converse about it and tell people where a particular element is located. Every group, so a group is a vertical column. Every group has a number. Okay, you may notice there are 2 numbering systems on this periodic table, as there are on any periodic table usually. And there is the original numbering system, which is called the AB system. So in that system, the first group is 1A, then 2A. These transition metals have very unusual properties, and so they're usually put in a group by themselves. And you'll notice that in the original numbering system, all of the groups have a B heading with them. And then to get back to the A group, you wait till you get to the nonmetals, and then you have 3A, 4A, 5A, etc. The new numbering system, newer, I should say, not really new, just labels the group sequentially from 1, 2, 3, 4, 5 through 12, and then 18. There are 18 groups. So just be aware of the 2 numbering systems. All right, so again, you need to know the terminology so that you can have a conversation about the periodic table. Each vertical column is called a group, okay? These are all groups. Each horizontal row is called a period. So going across from left to right, those are periods. There are 7 periods, and there are 18 groups. All right, the specific names of some of the groups are important because they're real commonly involved in chemical reactions. So group 1A, that's the first group to the far left of the periodic table, are called the alkaline metals. They're very reactive, probably the most reactive group on the periodic table. And I actually remember as a graduate student, this was unsafe and stupid of us, but I do remember that at night when we were doing research and nobody else was around, we'd grab a piece of sodium metal, go out to the nearby lake/pond, throw it in the water, and get an explosion that went 30 feet high of water. So group 1 metals are extremely reactive metals. Group 2A metals, okay, the second group from the left, are called alkaline earth metals. It's real easy to get these names mixed up because group 1A is alkali metals and group 2A is alkaline earth metals. So they are still reactive. They're not as explosively reactive as group 1A. And then the other group that's worth mentioning is group 7A. That's the next to the last group from the right, and I'll show you when a next periodic table comes up. They're nonmetals. They're called the halogens. So you have fluorine, chlorine, bromine, iodine, and astatine. These halogens are often involved in making salts. You have table salt, sodium chloride, and so they very often combine with alkali metals to make salts. All right, so here we go. The halogens are in group 7A. And now we're going to talk about noble gases. That's the group to the far right of the periodic table. Group 8A in the original numbering system, or group 18 in the more modern numbering system. Noble gases, they're called noble gases because they tend to be isolated. They don't tend to be involved in chemical reactions. They can be occasionally, but they take a lot more encouragement. They aren't very reactive. They're very stable. Okay, so the first one is helium. Of course, then we have neon, krypton. So these are the noble gases. All right, so just a few more slides and then we're done with this, but just to kind of ease you into the next topic, which is going to be chemical bonding and chemical reactions. We have so far talked about neutral atoms. Now, atoms as they exist on their own, or as we refer to in the periodic table, are neutral. That means there's no charge. And what that means is the number of protons equals the number of electrons. Of course, protons have a positive charge, electrons have a negative charge. So if you have equal numbers of them, you have a neutral atom. We're going to talk a little bit now about ions. An ion is simply a charged particle. Any particle that has any type of positive or negative charge. And in order to have a positive or negative charge, that means the number of protons in that ion do not equal the number of electrons. Okay? If you have more protons than electrons, let's say, okay, so if you've got 5 versus 4, you're going to have an overall extra proton and have a positive charge to the atom. So that's how you get an ion. You get an ion by either removing electrons or adding extra electrons. You do not get an ion by changing the number of protons, because what happens when you remove or add a proton? You have made an entirely new element. Okay? So it's all about the electrons when we're talking about ions. So positively charged ions, those that have more protons than electrons. Okay, for example, sodium ion. Remember, you may not remember, but back when I talked about metals, I said metals tend to like to lose electrons. So metals tend to become cations, because when they lose an electron, they get a positive charge. So positively charged ions are called cations, and I personally remember that because the T in cation, you can think of it as looking like a plus sign, and that's how I remember that. Negatively charged ions are called anions. Anions tend to come from nonmetals. Nonmetals, those atoms on the right side of the periodic table, are greedy for extra electrons, and when they get an extra electron, they get a negative charge and become an anion. Alrighty, so there are some elements that when they make an ion, make the same ion each time. And ions are formed typically when these elements are undergoing a chemical reaction. So I don't want you to think, for example, that all of these elements exist naturally with these charges. They don't. I'm just showing this to show you that when the elements do start to react by giving or taking electrons, these are the ions they make because they're particularly stable. So all of the group 1A or group 1 elements, when they make an ion, make a +1 charge cation. Group 2 elements, when they make an ion with a +2 charge. Transition metals are wonky as always. We'll talk about those later, but when they make cations or metals, so they make cations, the charges can vary. They have variable charge. Okay, so then on to group 3A, when they make ions, tend to make +3 ions. Group 4A, and that's the carbon group, tend to be resistant to making ions. If they did make ions, they could either have a +4 or a -4 charge. But more often than not, the group 4A is involved in, we'll discuss this later, but covalent bonding, which doesn't transfer electrons fully. All right, so then we kind of reverse it, and group 5A, the nitrogen group, tends to, when they make ions with a charge of -3. The oxygen group makes ions with -2, and I'm going to cross this out. And the halogens, group 7A, make ions with a charge of -1. The noble gases are not included because they are quite stable, quite unreactive, so they don't tend to make ions. You rarely see them with a charge. All right, so last slide here. I want you to have some type of understanding why, for example, elements in group 1A, when they chemically react, they tend to lose only one electron to form the +1 ion. You might ask yourself, well, and let's see, the group 2A elements, when they ionize, they will always get a +2 charge. And then talking about the halogens in group 7A, they will tend to gain one electron, which gives them a -1 charge. So why is that? Well, the reason is because by losing or gaining this specific number of electrons, these elements become very similar in their electronic structure to the noble gases. And that's because the noble gases are very stable and unreactive. And like everything in our world, most processes trend toward the state of lowest possible energy. And so any element, by losing or gaining electrons to become more like a noble gas, lowers its energy and becomes more stable. So let's look at one, for example. Let's see. Let's look at sodium. Okay. Sodium is in group 1A, and you'll learn a little bit later if you don't already remember, which means that it has one valence electron, one electron in its outermost energy shell. And so if sodium gives up that one valence electron in a chemical reaction, then electronically it becomes like, if you back up on the periodic table, the element before sodium is neon. So you may have to look at a periodic table to prove that to yourself. But it becomes like neon in its electronic structure. Neon is a noble gas. So let's look at one that's maybe a little bit easier to see. Let's see, over in the halogens, group 7A or group 17. If you look at fluorine, okay, fluorine's a nonmetal. Nonmetals tend to want to gain electrons. So when fluorine picks up one electron, it becomes very electronically similar to neon. Okay, and neon's a noble gas. And so that's what that table I showed you, and I said these are the charges that the different groups tend to get when they become an ion. That's something you should try to commit to memory. And that's it for this pre-recorded lecture.